You know, not all stars die the same way. In fact, their final chapter is pretty much written the moment they're born. So let's dive into the spectacular and sometimes incredibly violent final acts of a star's life.
This is a huge one, right? When you look up at the night sky, all those little points of light aren't going to be there forever. So what really happens when they run out of gas and that light finally goes out?
Well, it turns out the answer boils down to just one thing. It's mass. That's it. That one number decides everything. And it leads to two completely different endings. One is kind of quiet and graceful, and the other, a universe-shaking explosion. All right, so let's take a look at the first path, the one that's a little closer to home for us. This is what's in store for stars like our own sun. They're headed for a, believe it or not, pretty peaceful and beautiful retirement. So for billions and billions of years, a star like the sun is just kind of cruising along, totally stable, turning hydrogen into helium. But eventually, that hydrogen in the core runs out, and when it does, everything changes. The core shrinks down, gets super hot, and starts fusing the next thing on the menu, helium. And yeah, this is pretty much the beginning of the end.
Okay, so now that it's burning helium, that perfect balance it had for billions of years, astronomers call it hydrostatic equilibrium, is just gone. The star just puffs up, swelling into a massive red giant. And then over thousands of years, it just kind of gently shrugs off its outer layers. And this creates one of the most stunning things you can see in space, a beautiful, glowing planetary nebula.
So that beautiful cloud of gas drifts off into space. What's left? What's left is the core. Just this super hot, incredibly dense, burned out ember. We call it a white dwarf. And its future is simple. It's just going to cool down and fade away over trillions of years. A really quiet end to a very long life.
Okay, so that's the gentle retirement plan. But what about the real heavyweights of the universe? For the truly massive stars, the end is anything but gentle. It's the most spectacular, most violent explosion the universe has to offer, a supernova.
Think of the core of a massive star as this insane cosmic factory, just frantically burning through elements. After hydrogen, it's onto helium, which makes carbon. Then carbon makes oxygen. Oxygen makes silicon. Each step gets hotter and faster. We're talking billions of degrees here until it finally creates iron.
And iron is a dead end. See, fusing iron doesn't create energy, it actually takes energy. For a star, that's absolute poison. The engine at its core just switches off, instantly. And in a fraction of a second, gravity takes over and wins. The whole star just collapses in on itself, catastrophically.
Okay, hold on. Before we get to the big explosion, we've got to clear something up really quick. You've probably heard the word nova, right? Sounds similar, but it's a totally different thing. A nova is way smaller. It's just a little flare-up on the surface of a white dwarf. It's bright, for sure, but it's not even in the same league as a supernova.
And you can see the big differences right here. That core collapse of a massive star we were just talking about, that's a Type II supernova, and it leaves something behind. But a white dwarf can also cause a supernova, a Type I, if it gets too heavy. And in that case, the white dwarf is completely destroyed. Nothing left. So yeah, two totally different paths to two very different kinds of cosmic fireworks.
All right, so, boom. The massive star has gone supernova. Its guts are flying out across the galaxy. But what about the core that collapsed? What happened to it? Well, what's left is one of two things. And honestly, both are some of the most bizarre, most extreme objects in the entire universe. And you guessed it, it all comes back to mass. If that collapsing core has a mass somewhere between, say, 1.5 and 3 times the mass of our sun, it becomes a neutron star. But if the core is even heavier, then nothing, and I mean nothing, can stop the collapse. It becomes a black hole. Okay, let's talk about the neutron star first. Try to wrap your head around this. You take something with more mass than our entire sun, and you crush it down into a ball that's only a few kilometers wide. That's like cramming the sun into the size of a city. The density is just, it's mind-blowing.
So what happens when these super dense things spin really, really fast? Well, they can turn into these cosmic lighthouses, shooting out powerful beams of radiation. And if one of those beams happens to sweep across Earth as it spins, we see this perfect, regular pulse, and we call that a pulsar. It's pretty cool, actually. When Jocelyn Bell first discovered them back in 1967, the signal was so regular, so perfect, that for a minute they half-jokingly called it LGM-1, for little green mice.
But what if that core is even bigger? If it weighs in at more than about 3 times the mass of our sun, then even the insane pressure inside a neutron star isn't enough to stop gravity. The collapse just keeps going.
And that's how you get a black hole. It's an object with gravity so crushingly strong that to get away from it, you'd have to go faster than the speed of light. And since we know nothing can travel faster than light, well, nothing gets out. Not a thing, not even light.
Now, a black hole isn't like a planet. It doesn't have a solid surface you can stand on. Instead, what it has is this invisible boundary called the event horizon. You cross that line, and that's it. There is absolutely no coming back. It is literally the point of no return.
So how in the world do you measure the size of something you can't even see? Well, scientists use something called the Schwarzschild radius. It's basically the distance from the very center of the black hole out to that event horizon. And the bigger the black hole's mass, the bigger this radius is. It defines its whole zone of no escape.
Wow, so we've got these quiet fades and these insane explosions, leaving behind these cosmic ghosts like neutron stars and black holes. But what does any of this have to do with us, here on Earth? I mean, why should we care? The answer is pretty much everything.
Remember that crazy element factory we talked about inside massive stars? Well, in their final dying moments, that's where all the heavier elements were cooked up. I mean, just look around. The carbon that makes you, the oxygen you're breathing this very second, the iron in your blood, every single one of those atoms was forged inside a giant star that died a long, long time ago.
But here's the thing. All those amazing elements would just be locked away inside that star forever if it wasn't for the supernova. That incredibly violent death is also an incredible act of creation. It's what blasts all those life-giving elements out into the galaxy. It's like seeding the cosmos with the raw materials for new stars, new planets, and, eventually, us.
So, the next time you look up at the stars, just remember, you're not just looking at distant balls of gas. You're looking at your cosmic family tree, the ancestors that literally created the stuff you're made of. A star's death isn't really an end at all, is it? It's the ultimate beginning. It kind of makes you think. We always say our fate is written in the stars, but isn't it just amazing to realize that the star's fate is quite literally written in us?